We have the last talk of the session. It was to be given by Ryan Zeigler, but Jeremy Kent is filling in for him. The title of the talk is Micro CT of Apollo Samples. The laser pointer is that? Forward is that?
Great. Thank you. Okay, yes, Ryan was unable to be here today, so I will be filling in for him. All right, so just to get started, the basic goal of this presentation is just to show you that what we have done as a preliminary measure for micro CT work on Apollo lunar samples, and what we plan to do in the future, in the near future and beyond. So most of what I'm going to show you is applicable to not just Apollo samples, but other collections, especially Antarctic meteorites, but I'm going to focus mainly on Apollo samples. And what I'm going to show you has also been used already as primary justification for a micro CT scanner at Johnson Space Center, which has been approved, and we will be getting that at some point in the near future. And this is all part of a plan to kind of modernize the astromaterials curation process at JSC, not just for Apollo samples, but for all of our astromaterials, using new non-invasive or minimally invasive techniques. Now, the Apollo sample has been very well studied for decades now, and yet PIs still continue to clamor for new samples. Ryan says that this is because PIs are just a greedy lot, but those are his words, not mine, although he did tell me to say that. My interpretation is a little bit different. I understand that these samples have been very instrumental in our current understanding of everything there is to do with the lunar history and our knowledge of it. So, and they have been key to, these samples do have some limitations to them, though. There are only certain things that are available within them. Some of these samples are only available in small amounts, or even have been entirely used up. But there are possible new avenues for finding new samples, and these are potentially held with decades. These clasts have been not very useful for a lot of different types of scientific studies just because they were too small. Modern technologies have allowed, they now allow samples of that small size to be able to be used to provide to provide very high quality data. And as a result, we now need to go in and characterize all these clasts in all these polymorphic breccias. It's not something that we can really do very effectively with optical microscopy, because a lot of these clasts are not present at the surface of the samples, and also a lot of these samples themselves are coated in glass, so the clasts are covered. That's where micro CT comes in. So the process is basically very similar to a medical CT scan, but at higher energy, where X-ray beam is projected through the sample and collected by a detector behind, and that basically records a two-dimensional slice through the sample. Then the sample is rotated slightly, and another slice is recorded, and that continues until a full rotation of the sample has been made on the sample stage. And then all of those two-dimensional slices, generally there's going to be well over 1,000 of them, get integrated together to make a three-dimensional volume. So for our preliminary work, we have scanned 10 different samples at the Natural History Museum of London, and by we, I mean Ryan. And we profusely thank the Natural History Museum for all of their help in that regard. You can see the 10 samples here on the list, and the 3 that are underlined are ones that I'm going to show you a little bit more about in the coming slides. We've also done 1 CT scan at the University of Texas in Austin at their CT facilities. And we also thank them profusely for their help with that scan, as well as a wealth of advice and information that they've given us. So the first sample that I'll show you is Apollo 16 regolith breccia 60639. It's a pretty normal regolith breccia, except it has one unique feature. It's the only Apollo 16 sample with a pretty sizable clast of mid-titanium basalt within it. And I'll show you a movie right here, if I can start this movie. Now, as this is rotating, you can see right here, this is the exterior portion of that clast. And as we cut through the sample volume to try and find that clast on the interior and see how big it is, we see it starting to come into shape right here. And so it's actually quite a bit bigger than its exterior expression would have suggested. And right away we can start making out textural details of the clast. If we use some opacity, then we can begin to look at how big the clast itself is throughout the entire volume, and look at the presence of other high-density clasts throughout the rock as we continue to pan through it. And most of those other high-density materials would be olivines and pyroxenes. So once we've identified that particular clast and how big it is, where it's located in the rock, then we can do a secondary scan at a higher resolution on just a subvolume containing that in order to get a better resolution image of that particular clast of interest. And then we can create a model of just that particular clast, and we can see how big it is and how much sample can be made available for future allocations. The next sample I'll show you is sample 14321, another regolith breccia. And this one, okay, around the edges it's a little bit washed out on the screens up here. You may be able to see it better on the screens on the sides if you're able to see them. But where this little blue arrow here is pointing, there you can see the Teflon bagging that is around the outside of the sample. So these are primarily, these large Apollo samples are pristine. They're stored in nitrogen and kept sealed in nitrogen bagging. And we're able to maintain that pristinity even with the X-ray CT scan process. It can see right through multiple layers of Teflon bagging just like it's not even there. And so we're able to see that there are multiple different clasts within the sample. Many of them are not expressed on the surface at all. And we can also pick out metal grains and other materials. So the reason that the different materials show up differently is because of X-ray attenuation. As the X-rays are passing through the sample, higher density materials are going to attenuate the X-ray beam more so than lower density materials. And so the more attenuated the beam is, the lighter in color the material will be. So the higher density is light colored, and the lower density materials are darker in color. Because this is primarily tied to density, it's not a catch-all, so to speak. Materials that are of similar or equal density are not going to be easily resolved through this process. But for materials that do have some difference in them, you can set up the parameters of the scan and your visualization afterwards in order to to resolve what it is you're looking for. Like, for instance, you want to tell the difference between your pyroxenes and olivines within the rock, or you want to pick out all the zircons that may be present. There are other potential uses for micro-CT. It can be used for identifying individual mineral grains within igneous rocks and finding zircons, and also for measuring macroscopic porosity in lunar samples, like 15556 here. So we have one more video, if you can play this. So the gray exterior surface there is actually the exterior surface of the sample. It will transition into blue, and that is all of the solid material in the sample. The pink is now filling in all the void spaces, and once we transition to this, you'll see that there's a gradation. One side has much smaller bubbles in it than the other side does, and that really stands out in a three-dimensional view. So everything I've showed you here is applicable not just to the Apollo suite. It's certainly applicable to much of the Antarctic meteorite collection, and also it will be used for future sample return missions from the Moon, from Mars, OSIRIS-REx, and whatever else may come along. And this CT machine that we are getting will be also made available for external and internal users for purely research purposes. Yes, one more thing that we plan to do with the CT scan at the moment. It involves taking 3D photography of samples. So we take hundreds of photographs of a particular sample in a variety of orientations and inclinations around the sample, and combine those together to form a three-dimensional image, which can be manipulated in 3 dimensions on computer. And what we plan to do is overlay that 3-dimensional photographic image over top of a CT scan, and to make one single data set out of that, which we can then serve to the public as well for uses. So what do we do once we make the scans? Well, the details haven't been fully finalized yet, but the scan data would definitely be published online, and probably in a journal as well, in some manner similar to the ANSMET annual newsletter that announces new meteorites. And one other potential use just for curation purposes is these CT scans will allow us to make much more efficient use of the samples during allocation purposes. There will be less wasted material as we're cutting, because we're cutting in just the right place. So to wrap up, adding micro-CT as part of the curation capabilities will allow us to conserve the mass of our samples due to more efficient allocation processes, and it will also allow us to add new samples into the collection for allocation for scientific study. And also it's going to allow us to become more proficient at using CT processes for future uses. Thank you.
Larry?
Yes, Larry Taylor, University of Tennessee. Yeah, I applaud this technique. We had, if you might know, back in the late 70s and 80s, we had what we call consortia efforts. Mm-hmm. And what we did with 14305, 14321, a lot of those, is we would make a slice through it. Then we'd have to describe that slice, both sides of the slice. And then we'd have to write a little booklet describing every little grain in there and make that available to the public for a good length of time before we could actually go in and mine it. And I suspect that's what you're going to have to do here, because
Yes.
the people, some people are afraid of getting preferential treatment as far as getting into the sample.
Yes, that is definitely what we intend to do here. So as this data becomes available, once we have made these scans and characterized them, we will publish them, and once that data is published, scientists will be able to make their requests to CAPTEM, just as all of the other collections are handled, and from that point, CAPTEM will handle the allocation process.
Yeah, it's a very great process. I mean, we've been doing it for 20 years now on diamondiferous rocks, and it's really something good. It's what we used to call it a breccia pull apart back in the 80s. But now you can do the same breccia pull apart a whole lot easier.
Yep. Thank you.
We have an online question
Yes.
from Daniel Peters. His question is, by when will all the Apollo samples be scanned?
By when? Well, that's a good question, because we don't have a firm timeline yet on when the scanner will be available and fully online at JSC. That is in part dependent on finalizing the decision on which scanner we're going to get, and then also in part because we have to renovate a room in order to accommodate the scanner. We hope to have the renovations completed by the end of this year and the scanner delivered shortly thereafter, and hopefully by this time next year we'll be able to present some of the first scans.
Thank you. Thank you. Thank you all for your participation in the session. I'll make note of the fact that there is a session over lunch discussing geology of the SPA, which I would encourage anybody who has any interest to go to. Otherwise, thank you very much.